Hello, everybody. Welcome back to Mathematical Statistics. When I first uploaded lesson 12, I uploaded the wrong video. And once that was made apparent to me, I took it down and uploaded the right video, but that video had audio issues and I refilmed it and deleted and uploaded. And so in all the confusion, I seem to have lost a little bit of the material between what is now videos 11 and 12. So this should be fairly quick, but I do need to get something in here. And I want to thank Cal Burke 1737 for pointing this out. Let's go. At the end of video 11, I stated that convergence in probability is a stronger form of convergence than convergence in distribution. What this means is that if you have a sequence of random variables converging in probability to another random variable, then you necessarily have that sequence converging in distribution, but we do not have the other way around necessarily. So we're going to prove this, and then after this, we'll see a quick example of the other way around not holding, and we will be caught up. I have a convergence in probability result here, so I'm going to need an epsilon. And because I want to show convergence in distribution, I'm going to need a notation for the CDF of these random variables and the CDF for this one. So let's let fxn be the probability that xn is less than or equal to x. And then we'll do the same thing for f of x being the probability, or CDF for x, the probability that it's less than or equal to x. I want to show that the limit of these functions approaches this function, but it doesn't have to be true everywhere. It only has to be true at points of continuity of this limiting CDF. So let's grab one of those. I'm going to let x be a point of continuity of the CDF f of x. We want to show convergence in distribution for the sequence xn, so let's consider that CDF for xn. This, of course, again, is the probability that xn is less than or equal to x. And I would like to bring the random variable x into this line. So what I'm about to do is this. Suppose I ask you the probability that if I roll a fair six-sided die, I get an even number. Sometimes in probability, it's convenient to bring in another event. Not in that case, I think we can compute that probability. However, the probability we get an even number on that six-sided die can be written as the probability we get an even number, and also we flip a coin and get heads on the coin, or the disjoint event probability that we get an even number on the die and get a tail when we flip the coin. So we can add those two probabilities together to get the probability we get an even number on the six-sided die. So that's the kind of thing I'm going to do here. I'm going to rewrite this as the probability that xn is less than or equal to x, and comma, x is less than or equal to little x plus epsilon, plus or the disjoint event probability that xn is less than or equal to x and x is greater than x plus epsilon. So I dragged in another event because it's going to make this problem, it's going to be convenient for us. Let's look at this last probability right here. If you imagine what's going on like a number line, and you put down our number x, and then an x plus epsilon, where epsilon is positive, the final probability that I have over here says that xn is somewhere down here and x is somewhere up here. So this implies that xn and x are more than epsilon apart. It's more specific than that. It is talking about how things are positioned with relation to this little x. But if this event happens, I can definitely say that xn and x are more than epsilon apart. But if xn and x are more than epsilon apart, I don't necessarily have this event happening. So this event right here is contained in the event where xn and x are more than epsilon apart. In other words, I can write this probability over here as less than or equal to the probability that the absolute value of xn minus x is greater than epsilon. Again, if this happens, then this happens, but not the other way around. So it's like having an event A contained in an event B, then the probability that A happens is less than or equal to the probability that B happens. I am going to write the entire next line. I'm going to put something bigger here. So not only am I going to use this in place of this, but I am going to bound this above. I'm going to put something bigger, a bigger probability here. And I can do that very simply by dropping one of these two events inside. The remaining probability is going to be larger because it's harder for both things to happen than it is for any one of them to happen. So any one of them happening would have a larger probability. So in conclusion, this entire line I can write as less than or equal to the probability that x is less than or equal to x plus epsilon plus the probability that absolute xn minus x is greater than epsilon. So again, I have bounded this term above by this term, and I have bounded this term above by this term. One more time, up here, I need two things to happen, and that happens with some probability. But if I only need one of them to happen, which is happening over here, that's going to be easier to do. So a higher probability. Okay, so what I have here is the CDF for just x, which is capital F, evaluated at x plus epsilon, plus something that looks like the main part of a convergence in probability statement. I am going to want to be taking the limit as n goes to infinity of this, and I could take the limit of this stuff. Now, because xn is converging in probability to x, this term is going to go to 0 because the distance between them is not going to be above some number as n gets large. But this will only give us that this CDF is less than or equal to something, and I want to know its actual limit. So I'm going to do kind of a squeeze theorem thing. I'm going to start again and try to get the f and x bounded below. So kind of looking at what I have here, I'm going to start with something that looks like this, but not. Consider, if you will, capital F of x minus epsilon. This is the probability that the random variable x is less than or equal to x minus epsilon. I'm going to bring in this event. So let's write this as the probability that x is less than or equal to x minus epsilon and xn is less than or equal to x, plus the disjoint event probability that x is less than or equal to x minus epsilon and xn is greater than x. Consider this n term again. If we drew another picture, we've got some x, and then we have some x minus epsilon down below x. And we're saying that the random variable xn is up here, and x is down here. So xn and x are more than epsilon apart. But just xn and x being more than epsilon apart does not mean they're specifically to the left of this and to the right of this. So this is a very specific case of xn and x being more than epsilon apart. And if we want to look at that event, we will have a higher probability of that happening. So this is less than or equal to the probability absolute xn minus x is greater than epsilon. Because one more time, if this happens, then this has happened, but not the other way around. Also, I want to bound this term. Before, we had this term, and we dropped this. Now I'm going to drop kind of the opposite, if you will. I am going to go to the bottom here. This whole thing is less than or equal to the probability that xn is less than or equal to x. So that's an upper bound for this first term because I dropped one of the events in there. And the second one we just talked about, I'm going to write it as the probability that xn minus x is greater than epsilon. That first term there is, of course, the CDF for xn evaluated at x. And the second one is something that is going to go to 0 as n goes to infinity because xn is converging to x. Let's put both of these lines together. So this guy and this guy. And I'm going to put fnx below this thing. And then I'm going to take this minus this. Well, you'll see what I'm going to do. I think I'm making it worse by trying to say all that. What we now know is that capital F of x minus epsilon minus the probability that xn minus x is greater than epsilon. This is less than or equal to fn of x. So that is this sort of reorganized. And if you go back up to the previous line, we did say that fnx is less than or equal to f of x plus epsilon plus the probability absolute xn minus x is greater than epsilon. Let's let n go to infinity all the way across. So a limit and a limit and a limit, which I'm kind of too lazy to write. On the left side, as n goes to infinity, this term isn't moving, it's just right there. This term is going to 0 because xn is converging to x in probability. The middle term, I don't know what that's going to. That's kind of what I want to find. We would like it to be capital Fx. That's what we're trying to show, but don't say that because we don't know that yet. And actually, we don't even know that this limit exists. But let's continue to the limit on the right-hand side. As n goes to infinity, that first term just sits there, and the second term goes to 0. So real quick, let me just get rid of that 0, make this a little nicer looking. Now again, at this point, I don't even know that this limit exists, but what I'm going to do is I'm going to take our arbitrarily chosen epsilon. It needs to be something positive, and I'm going to let it go down to 0. What will happen as epsilon goes down to 0 is that this will approach capital F of x. And here is where I am using the fact that x is a point of continuity of that CDF. Because if we have maybe at some x and we are a little bit to the left and maybe we have a jump, then the f of x for this picture is up here. So if I looked at this term and let epsilon shrink to 0, I would approach f of x. But if I look at this term and let epsilon shrink to 0, I will be approaching this lower point, not f of x. So I do get f of x because x was chosen to be a point of continuity of that limiting CDF. In the middle, there's no epsilon, so let's just rewrite that. And on the right, as epsilon goes to 0, we get f of x. So now we do have this limit, which we weren't sure it existed until this point. It is between f of x and f of x. So we've got like a squeeze theorem happening here. This implies that not only does this limit exist, but it is equal to capital F of x. And that's what we wanted to show. This is giving us the result that xn converges in distribution to x. So we are done with this proof. I did promise you a counterexample. So here is an example of xn converging in distribution to x, but xn not converging in probability to x. Consider a sequence of random variables, x1, x2, etc. IID, so independent with a common distribution, I'm going to make this a very simple distribution. I'm going to let the random variables only take on the values -1 and 1. So the probability that xi is equal to plus or -1 is going to be 1/2. And this distribution does not change as I changes. So they all have their IID. I'm going to let a random variable x be independent of all of those x's with the same distribution. So the probability that x is equal to plus or -1 is also going to be 1/2. I claim that these random variables are converging in distribution to this random variable. And to show that, I need to write down, actually, I don't need to write it down, but we need the CDFs for this to approach the CDF for this. All of the CDFs are exactly the same. Here is a -1. Let's just throw in 0. Why not? A +1. The CDF for any one of all of these random variables, for x1, x2, x3, on up, and even the random variable x, it is going to have no probability of being down here. But when it hits -1, it will jump up to a height of 1/2. And then it will stay flat and it will not accumulate any more probability until it hits 1. And at that point, it will jump up another height of 1/2 and be at a height of 1. So both of these jumps have height 1/2, and the CDF for not only x, but every one of these xi is a step function like this. And it does not change as n changes. It's the exact same CDF. So we do have, even if I don't feel like writing this out in a closed form piecewise expression, we do have the limit as n goes to infinity of f n x equaling f of x, because this function looks like this for every single n, and so does this. So there's no n moving. So it's a kind of trivial limit. And we do have that xn is converging in distribution to x, which is what I want for this example. It's an example where we do have convergence in distribution, but I claim we do not have convergence in probability. So for convergence in probability, you need a certain limit to hold for all epsilon, but to show it does not converge in probability, it is enough to exhibit some epsilon. So consider the probability that xn minus x is greater than or equal to 2. Remember, we can use strict inequalities or non-strict inequalities when trying to show convergence in probability. If this bothers you, then I want you to replace this, because we're used to saying maybe greater than epsilon. You can replace this with greater than like 1.9 and proceed in the same way. But it doesn't matter. If xn is supposed to be converging to x in probability, then this distance should not be greater than or equal to 2 as n goes to infinity. In other words, when we take the limit of this as n goes to infinity, we do want to get 0. Note that all of the random variables here take on the values plus and -1. So really the difference between them is going to be 0 or +2 or -2. So greater than or equal to 2 is actually going to happen whenever this is equal to 2. Again, if you made this strictly greater than 1.9, then this line would still be correct. This distance between xn and x being equal to 2 happens if xn is equal to 1 and x is equal to -1, or we get a disjoint event where xn is equal to -1 and x is equal to 1. Those are the two ways where this can happen for this particular sequence of variables. I did assume that all the xn's were independent of each other and also independent of x. So by independence, I get to break this up into a product over here and a product for the second term as well. All of these probabilities are equal to 1/2. So we get 1/2 for this probability. But if we have a convergence in probability, if we take the limit of the thing I just circled, we need this to go to 0, no matter what epsilon we've chosen here. And this is not going to 0. It's not going anywhere. So we have exhibited an epsilon where we do not get this limit to go to 0. And this means that we do not have, in this case, convergence in probability to x. So there is our counterexample. Hopefully, I have fully patched the missing information between lessons 11 and 12. So I'll see you in 12.